This is the fourth lecture for Chapter 3 for ODE, and in this lecture I will work through the Hamiltonian system of this simple undamped pendulum. So here's a sketch of the pendulum, which I even sort of did myself, although it looks like it's more of an ellipse than a circle there, so I don't know what I did. Okay, so what we have is a point mass right here. This is your point mass right here, and it's held by a rod of length L, and the mass of the rod is neglected. Mass of the rod is neglected. Right? Of course, gravity's acting on this pendulum. It's free to rotate about this point completely 360 degrees. The path is this arc length right here, which is the length of the pendulum times theta, theta being the angle off of the downward direction. There's a force due to gravity, also acting in downward direction, minus mg times the sine of theta, because it's going to be in this direction. So that's the pendulum. There are much more complicated pendulums. There's dual ones where you have all kinds of things turning. There's pendulums that are moving, but just with the simple pendulum we're going to get very interesting results. So if we start by taking all the forces into account, well, not all of them, but some of the more basic ones, we have, of course, Newton's law, which is mass times acceleration, and we have to use that arc length. Remember the arc length S, that's a path length on it, which is length times theta. The length of the rod is not changing in our simple pendulum, so we just have that the force equals mass times the length of the pendulum times the second derivative of the angle. We can take resistance to motion into account. That could be some kind of air resistance, or if the pendulum's in water you might have some resistance, and if you put that in this terms, I'm going to put it in, I'm going to take it off. Okay, there are many ways to include resistance to motion. It can be included as the first derivative squared, the second derivative. There's different ways to include it. This is the most simple way to include resistance to motion. Right. Then there's the force due to gravity that we wrote on the sketch. So now if we equate all of these terms, we end up with a second order nonlinear equation for the pendulum. What's nonlinear about it? Well, right here. So here the terms are all equated, and then I like to write things in a standard form. Now I've noticed on some of the work and exams that were turned in that people tend to leave these constants, these coefficients, multiplying the second derivative. It's better to divide them. If you learned that, you learned that from a different class. You didn't learn that from me, because you should divide these out and have the only coefficient here is 1. Okay, well, I could write that in for you. The reason for that is that these terms will have physical significance. When you have this sitting out here, it complicates the solution, and you don't get these terms in this form, which are your attenuation, and also turn out to be things like your the frequency. So, all right, so here it is in standard form, and now we're going to write this as a system. We have two things. We'll write theta as the first variable. As the first variable, second variable will be a velocity. Okay, and here's our system. Now, this is not Hamiltonian as it stands, so I'm going to have to dump something, and I will dump that damping term. I just put the damping in so that you could just sort of see it in general, in case you ever want to do that problem. That might come up sometime, you know, if you do dissipative systems. But here we're going to look at the Hamiltonian system, which is the undamped pendulum, and here it is. There's a system for it. That beta, I just set the beta equal to 0, and this is what I get. Does it satisfy the condition? Okay, to satisfy the condition, this is my F of, and this is my G. So I would have to take df with respect to theta, which is 0, and I have to compare that with the derivative with respect to v of g. But that's also 0, so they agree, so it is a Hamiltonian system, and we can proceed with the tools that we developed in the previous lecture. Now we're going to construct the Hamiltonian again. First we're going to integrate, and we'll end up with, we're integrating the integrating of f of theta v with respect to v. Did I do that right? Well, we end up with v squared over 2 plus this function of theta, this function of theta, which is not defined. So we're going to take the derivative of everything with respect to theta and rearrange. Remember, dh by d theta is minus g of L times sine theta, but then there's a negative sign in there, so here's what we end up. Oh, sorry. Here's what we end up here. You can work through these steps. Okay. And that will equal the derivative of v with respect to theta and the derivative of v squared over 2 with respect to theta. Of course, this goes to 0, so we end up with, let me write that out here, d phi by d theta, phi by d, try it again. Okay, phi of theta, get my lines right, will be the integral of the derivative of v with respect to theta times d theta. Okay, and that's all I have here, because this is 0, is going to be the integral of g over L times the sine of theta d theta, which gives me minus g over L cosine theta plus a constant c, and I set that c to 0. So adding, now I have a specification of that. I already had this term, so here's my Hamiltonian, v squared over 2 minus g over L times the cosine of theta. So now I have a form for a nice closed form solution for the Hamiltonian for this system. So I need to look at the equilibrium points. Remember what the Hamiltonian was. Hamiltonian of so if I take the partial with respect to v, it's just going to give me v. The partial with respect to theta gives me g over L times sine theta. I want both of these to be 0. The first solution vanishes for v equals 0. For the second solution, this will vanish for multiples of pi, so that the sine, sine pi, sine 2 pi, sine 3 pi, etc. are all 0. So these are the critical points of the Hamiltonian. Okay, theta can be 0, plus or minus 1 pi, plus or minus 2 pi, and all the values for v at equilibrium are all going to be 0. Now let's look at the Hamiltonian to see how the system is going to behave at these equilibrium points. So this is a Hamiltonian system. So I know from the previous lecture that the eigenvalues are plus or minus the square root of alpha squared plus beta gamma. Here's alpha, which is a mixed partial derivative of h. In this case that will be 0. Here's beta, which turns out to be 1. And gamma is minus g over L times cosine theta. So I substitute this into the equation, and here are my eigenvalues. We see a negative sign here, and initially you might think that this is a case for complex eigenvalues, but we have to look also at the cosine of theta. So when cosine theta is negative, this is going to be positive. So all of those, that big list, that infinitely long list of equilibrium points really reduces to just two cases. The case in which cosine theta is positive, and those will be complex, in the case when cosine theta is negative, and those are going to be saddles. So let's look at the first case. In this case, theta is going to be 0, plus or minus 2 pi, 4 pi. The cosine term will be positive. So the eigenvalue, it'll be positive, it's going to be plus 1. So the eigenvalue so this is plus or minus I root g over L, and this will be a center at these values of theta. For the other case, cosine is negative, it's a negative 1, so this becomes plus or minus the square root of g over L. Well, one's positive, one's negative, they happen to be identical, and that gives you two distinct real eigenvalues, so this result is going to be a saddle. And this is the classic result for the simple undamped pendulum. It's a nonlinear system. So what do we see here? We see, first of all, these centers. You can see the center here. See the centers here. These are nested, in this case, circles because of we're choosing g over L. And they're about these values of pi for which cosine of theta is positive. And then here we see the saddles. Saddle here, here's a saddle here. What does it really matter that it's 2 pi, 3 pi, 4 pi? It's as though you swung the pendulum a bunch of times, so you don't really have to worry about it. That's just a solution. So what do these solution curves mean? They're actually fairly interesting. Okay. Now, this is velocity and this is angle. Okay, so I'm going to start here with an angle of 0. That means the pendulum is hanging down like this. If the velocity is negative from here, then I'm moving over in this direction. Now how far do I move? Well, to whatever this theta is, let's say it's pi over 2, and I move up this high. Okay, so I went in this direction because I was going along this curve. Now the velocity is positive. Just means I'm going to the other direction. So I go in this other direction all the way over to here. I don't know what I do. There's something wrong. At any rate, I'm coming back and forth, oscillating about this position, the 0 position here. What I did, I started here, I went in this direction, so then I come back over here, I go all the way through 0, come back over to this side. I'm sorry, let me start that one again. I think I started in the wrong spot. Okay, I'm going to start here. I'm going to go in this direction, then I'm going to swing back, then I'm going to go around here, and I'm going to come back to the starting point. So that means I came over to here, to whatever value of theta this is, theta prime. So this is here, theta prime. And then I go back in this direction to theta prime, and then I go back in this direction, and I continue to go back and forth along this curve, and that's as though you're sweeping out around this circle. Of course, here you didn't go so far, maybe you only went like this. Alright? Okay, where is pi? Here's our system, here's theta, pi is up here. So at this saddle, we'll start here. The pendulum swings all the way to the vertical upright position, which is pi. Then it turns around, and now it's swinging to the other direction, all the way up to pi again, and then it comes all the way back down and repeats the process. And that's what's going on at this saddle. Okay, so that's, you have the centers here, you have the saddle here. What about these curves? In these curves, the solution is actually moving here, and the pendulum is swinging around and around and around and around, and it's not retracing its steps. See, in this case, it's always be going to the right. In this case, it's always be circling. Wait a minute. I'm sorry, I got right and left mixed up. At any rate, this would be going clockwise, and this would be going counterclockwise. Okay, that's better. So this is a classical result for the undamped pendulum. You probably see this graph on the final, and you can see examples of this in the book, in the textbook, and also you can Google this on the internet and you can see this result there as well. So this is the last lecture for that chapter 3. These have been very interesting examples. We did van der Waals with that strange attractor. Here's a nonlinear pendulum with this very interesting phase portrait. Okay, and in the homework you're looking at the Lorentz equation. As I said before, nonlinear systems merit quite a bit more study than what we've given them here. In fact, those are some of the most interesting systems that you're going to study when you get into physics and into engineering. So that's the end of the lectures for this class. As far as the Laplace transforms, it's pretty much, you can look at those in the book. The only things you have to that might be new to you are the Dirac delta function, and you should already know the Heaviside function. And you can see how the transforms go. Actually, transforms are pretty simple. The only problem is the partial fractions. I'll try to post something on partial fractions. You know, it's easy enough to get down to this, to use the Laplace transforms on the system. That's easy enough to move over to your solutions, but then you have to undo this by using partial fractions. If you have any questions on the written lectures or on these video lectures, you can contact me. Email works the best. Thank you.